Okay, so hello everyone. My name is Lohit Kwan and this is live session 8. So, so let me join from my tab. So today we will talk about Lagrange interpolation, Newton's divided difference interpolation and spline interpolation. So before dive into the problems, first I will give you a brief idea about those techniques you already know about these ideas, but anyway I will just cover it just very briefly. Then I will start doing calculations. I have prepared total maybe 15, 16 questions from the previous year assignments and from other sources. So we will practice those things. So let me join from my tab. Just a moment. Yeah, sorry for the delay. So I will start. I will share my screen. Okay. So first we will. So so we have total three major topics today. First is the Lagrange interpolation, then the Newton divided difference, and third is the spline interpolation. So first I will give some brief ideas about this topic. So first let's start with the Lagrange interpolation. So suppose you have some data points y0, x1, y1, x and y, and so you have total n plus 1 data points. Okay. So the So what can be your interpolating function? So one guess that can be, suppose, if I have total n plus one data points, the polynomial is will be of order n, the order n or less, if we want to get a unique polynomial. So Pn of x, we can write it as some Li of x multiplied by yi, where I is varying from I equal to 0 to n. Now, what is Li? Li is an weighting function. Now, so what is the definition of LIX? Such that your Pn of xi is equal to yi exactly. So this is some wild guess. So I have some data points like this over here. This is one data point, one data point. My polynomial can be anything, but at this xi, the value of the polynomial should be equal to yi. So this is the this is my only criteria. Now, so in this case, so what we have to make some choices about the Li of x. Hmm. So what can be that choice? That is Li of xi. This should be equal to 1. And see if this is just check if this is correct. If this is 1 at this point, then Pn of xi is equal to yi, right? And if it is 0 at any other point, then the value will be 0. So how to say, so if I want to say it simply, suppose I have three data point A, C, and I want to have a polynomial which is 0 at B and C, but 1 at x equal to A. So what can be the choice? One obvious choice is x minus b into x minus c. See that if f of b is equal to 0, f of c is equal to 0. At any other point, this value is 0. Hmm? But if I put f equal to a, then this value is not equal to 1. This value is a minus b into a minus c. So to make it a unity. So what can be the choice? Suppose gx is the modified polynomial, and it will be x minus b, x minus c divided by a minus b into a minus c. The same idea we will be following in the here in case of Lagrange interpolation. Okay, so suppose I have three data points. My fitting polynomial, it will be p2 of x. P2 of x will be equal to L0 of x y naught plus L1 of x y1 plus L2 of x y2. Now what will be the L naught of x? Now how to remember? So you need to remember this formula. So I remember it is in this way. Here it is 0, so it will start with 0, and it will not take x0 in x0 in any other term. So it will be x0 minus x1, x0 minus x2, not x0 minus x0. Otherwise it will be infinite. And in the numerator, replace x naught by x minus x1, x minus x2. Similarly, L1 of x equal to, here it is 1. So in the denominator it will be x1 minus x naught, x1 minus x2. So in place of x1, replace x. It will be x minus x naught, x minus x2, and similarly you need to write L2 as well. Okay. So 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 you can see that if I put L naught of x naught, L naught of x naught equal to 1, but L naught of x1 is equal to 0, L naught of x2 is equal to 0. The same thing will happen for this or for other two also. L1 of x1 is equal to 1, but L1 of x naught and L1 of x2 is equal to 0. All right. So that means if I want to plot this thing, suppose these are my data. Suppose this is my x naught. So L naught of x naught equal to 1. This value is equal to 1. and any other point, suppose this is, sorry, so this is suppose x naught, this is my x1, and I am plotting L1 of x. At any other point it is 0, it is x2, it is 0, it is x3 equal to 0. So it will follow in this way. So we need to remember these formulas because we will be applying it repeatedly while solving the problem. Now, one interesting observation is related to this Lagrange interpolation. Just a moment. So now the problem is, mm, right. So here this is an exercise. Okay, a short exercise. So here I have L0. So here I have three data points. Suppose the T0, F0, T1, F1, T2, F2. So I can fit a second order polynomial P2 of t. Now I need to show that I equal to 0 to t, Li of t is equal to 1. I need to show that. So how can we proceed? So while solving the example, I will show you that this is essentially the idea for whatever the size of the data sets. This summation will be always equal to 1. Now, here I will solve it for the three data points. So let's write down L naught, L1 and L2. So what is L naught of t? So remember what I have said, that in the first, so you can start, you can memorize the formula like this. So t naught minus t1, t naught minus t2, and t minus t1 multiplied by t minus t2. Similarly, L1 of t is equal to, so it is starting with 1, so it will be t1 minus t0, t1 minus t2, t minus t0, t minus t2, and L2 of t, this is equal to t2 minus t0, t2 minus t1, t minus t0, and t minus t1. Now to prove that, I need to add this add this three expressions. So we can clearly see that there will be some common factor in the denominator, and I need to just do some algebraic manipulation, and after that we will see if it is 1 or not. So if I just write L naught t plus L1 of t plus L2 of t, I can I can take these as common. So this is T0 minus T1, T0 minus T2, and T1 minus T2. It will be the common. So T minus T1, T minus T2, T1 minus T2. It is coming from the first term from L0. From the second term, I don't have sufficient space. Maybe I will T minus T0, T minus T2, T, sorry, this is T1 minus T2, it is T0 minus T2. This is coming from the L1T, it is coming from L0T, plus some term will come from the L2T as well. It is T minus T0, T minus T1 multiplied by T0 minus T1. Now suppose let us take that T minus T1 equal to A, T minus T2 is equal to B, and T minus T0 is equal to C. Okay, so this first term will be A into B and T1 minus T2. How can we write it? We can write it in this way. See that So it is inside a brace. So t minus t2 minus t minus of t1. I can write it in this way. T1 minus T2 is, I can write it at like T minus T2 minus T minus of T1. Just I just wanted to convert. I just want to simplify these terms in terms of A, B, and C, and then we will see what happens. T minus T naught is equal to C, no problem, into B. Similarly, we will see that T naught minus T2. You can write it like T minus T2. It is minus of T minus T0. Plus t minus t naught is again C, t minus t1 is A, and t naught minus t1. So t minus t1 minus of t minus t is naught. And in the denominator, what will I have? It is t naught minus t1. So t is t naught minus t1 is what? C minus of A. T naught minus t1. No, t naught minus t1 is A minus C. It is A minus of C. Then T naught minus T2, it is B minus of C, and T1 minus T2 is B minus A. Okay. Now we need to work on the numerator. So it will, first term will be AB into B minus A minus BC into B minus C plus AC into C minus A. Sorry, AC into A minus C, because T minus T1 is A. So here and here, this is the A minus C, B minus C, B minus A. Right. So what I can do, I will keep this term like this and operate on these terms. Okay. So it will be AB square minus of A square B minus B square C plus B C square plus AC into A minus C. Hmm. So divided by A minus C, B minus C, and B minus A. So let me take A minus C, a common factor. It will be AC. So the first term is B square. So plus B square A. And it is giving me automatically minus B square C. So this term is obtained. So if I take just plus B square, it is giving me AB square minus B square C. Okay. Then what will be the next term? The next term I think should be minus AB. Minus AB gives me back minus A square B and a plus ABC. And plus ABC is not in the expression. So I need to take minus plus ABC. So I need minus ABC. So minus BC. So this minus BC will give me minus ABC plus BC squared. Plus BC squared. Yeah. So I have got all the terms. So it will be divided by A minus C, B minus C, B minus of A. It is equal to A minus C multiplied by A into C minus B plus B into B minus C. So you can clearly see that we will get a common factor here as well. So if you just do some simple algebra, you will find that you are getting this as in the numerator, which is exactly same as the denominator. and this value is equal to 1. So summation of I equal to 0 to 2 L0 of t is equal to 1. Okay, so this is an interesting exercise. So now now I hope that how we are getting the idea of finding the Lagrangian interpolation function is pretty clear so far. Now you will see that when we will work on the problems using this Lagrange interpolation, you will find that it is quite difficult. I mean, the expressions are large, so you need to work. You need to do a good amount of work to find the exact or complete solution. But there is an interesting idea, but there is a better and easier way to solve this kind of problem when the step size is not uniform. That means we solve using the Newton forward difference or backward difference formula when there is a constant step size. Here for Lagrange interpolation, the step size is not uniform. Also, there is another method where the step size is not uniform, but we can solve this kind of problem quite easily. So that is Newton's divided difference interpolation, DD. Okay. So what is the idea? Suppose you have three data points: x naught, y naught, x1, y1, and x2, y2. Now, so what will be the polynomial? We know it will be quadratic polynomials because I have total three data points. Okay. So one method can we so one fitting polynomial can be p2x equal to ax square plus bx plus c. This is a very obvious choice. So in the last lecture, I have solved probably two problems using this technique. Okay, this is direct method. I have three unknowns. If I put the value of x naught square plus bx naught plus c will be equal to y naught, and similarly for x1 and x2. So finally, we will have finally the three unknowns and three equations. So I can solve this. So this is a basic idea. But in order to solve the equations, I need to solve three simultaneous equations. Okay. But is there any? But the question is there any other way by which we can simplify our task? Here comes the divided difference formula. So here I can approximate the same function. I will get the same polynomial function like this: b naught plus b1 x minus x naught plus b2 x2 sorry x minus x naught x minus x1. Now see, if I put x equal to x naught, then I don't need to solve the third equation. I will automatically get the value of b naught because this will be 0, this will be 0. So I will automatically get the value of b naught. Now then if I put x equal to x1, this will be non-zero, but I have already got the value. But I need this will be x1 minus x0, a non-zero term, but this term will be 0. So from here, this is known. I will get the value of b1. Similarly, if I put x2, three of them will be non-zero, and I will get b2. And I have already known b0 and b1. This is exactly similar to the back substitution method that we learned in the earlier classes. So after Gauss elimination, we need to do the back substitution to solve the problem. This is exactly same technique, and you can show it very easily actually. So let's write these functions write the function for x0, x1, and x2. So in case of x naught, this will be b naught plus b. In case of x equal to x naught, yeah. So b1 x naught minus x naught plus b2 x naught minus x naught minus x1 is equal to y naught. This implies b naught equal to y naught. This is equation 1. The second equation is b naught Now put x equal to x1. B1 into x1 minus x naught, and this term will be 0. I will not write it here, and this will be right hand side is y1. This is 2. Now if I put x equal to x2, b naught plus b1, it will be x2 minus x naught. Plus b2, it will be x2 minus x naught, and x2 minus x1 is will be equal to y2, 3. Now in matrix notation, how can we write it? I can write it like this. So I will arrange the equation like this. First equation 3 will come, then equation 2 will come, then equation 1 will come. So the first equation, so this is coming from equation 3, this is coming from equation 2, okay, and it will be just 0, 0, 1, and it will be multiplied with b2, b1, and b0. You can see. So I am starting with this b2 into this b1 into this plus b0 is equal to right hand side y2, y1, y0. You can see that it is just like what we get after Gauss elimination process. This is exactly the same thing. So this is just the back substitution technique we are using. So here your b0 is equal to y0, b1 into x1 minus x naught plus b0 is equal to y1, and b0 is y0. So b1 equal to y1 minus y naught by x1 minus x naught. Okay, and for the third equation, x2 minus x naught, x2 minus x1 b2 plus x2 minus x naught b1 plus b0 is equal to y2. So this implies x2 minus x naught, x2 minus x1 b2 plus x2 minus x naught multiplied by y1 by y naught, x1 minus x naught is equal to b naught is y naught, y2 minus y naught. So I can take x2 minus x naught common. So I will divide it. I will divide everything by this term. So b2 is equal to y2 minus y naught, x2 minus x naught x1 minus y1 minus x1 x1 minus x naught. Okay. So this way you will be able to find these types of expression. Okay. So this is the basic idea of the Newton divided difference. Now, one interesting thing about the Newton's divided difference that I will do while I will explain while solving the examples, that you need to go through all this complicated calculation. If you have a table of x and y, some data points, just like the Newton's forward or backward difference, you will be able to solve. You can build a table of Newton of the divided difference, and you can very easily find this value of b0, b1, b2, etc. Okay, the idea is very simple. You just need to build a table. That's so this technique makes it much simpler compared to the Lagrange interpolation technique. Okay, so I will talk about the spline later. But first, let me solve few questions regarding this Lagrange interpolation and this Newton's divided difference. Okay, just a moment. Okay. So this first question is a conceptual question. So it says that if a polynomial has a degree of m and has m plus 1 zeros, then the polynomial is, you need to find a correct answer. Okay. Now let us take a simplified example because this m is a general number. So let us take n equal to 2. Okay. So that means I have total 3 data points: x naught, y naught, x1, y1, x2, y2. Okay. So and the polynomial can be, so let us take just the direct method thing. So some fx equal to ax square plus bx plus c. Okay. Now it has total m plus 1 zero. Suppose this will give you the total zeros. Okay, if I put these points, so one can be ax naught square to bx naught plus c. It is giving me 1 0. Okay, so suppose these are the roots of these polynomials. Similarly, ax1 square plus bx1 plus c equal to 0, and ax2 square plus bx2 plus c equals to 0. Then what does it imply? It will be only true when a equal to b equal to c equal to 0. It implies what? My initial guess of the polynomial was ax square plus bx plus c. So if a equal to b equal to c equal to 0, then your f of x is equal to 0 everywhere. So this option is correct. Okay. Now the next question. Right. So here we will use. You will see how can we use the table. Now here we will see how can we use the divided difference table to obtain the value of b0, b1, and b2. Okay. So let me write over here the x and y. This 10, 15, 25. This is 4, 9, 25. So I remember in this manner. So I will share you what I. So this value is corresponds to b0. That is the initial y. Because if you put, so this is my x0. Okay. Because if you put x0, this 10 is x0. 15 is x1. If you put x equal to x naught, this value will be 0, this value will be 0, so it will be simply y of 0. So I am getting that value, y of 0. Okay, so this value is b0. Now I will take the difference. So this term will be 9 by 4 divided by 15 minus 10, just similar to the forward difference. 9 minus 4 by 15 minus 10. This value is equal to 5 by 5 is equal to 1. This value is 1. Okay. Now I will do this thing again. 25 minus 9 by 25 minus 15. Right. So this is 16 by 10 is equal to 1.6. Now I have only 2. Now I will divide this and this. But so the numerator is easy. So 1 minus 1.6 divided by what? So now here I remember like this. I follow the direction of arrow. So it is going from here, then it is going from here, and then it is landing. So you need to follow the arrow until you land on the x, on the x column. Okay. So I am following this arrow. Then first it is 1, then it is 4, and corresponding x is 10. Okay, for 1. So it is, sorry, so I am writing it wrong. It should be 0.6 minus 1. Okay, divided by, so 1.6, 1, so first term is 1.6, so 1.6, follow the arrow. So this, then this it is coming from here, and the corresponding x is 25. So 25 minus, again this one, follow the arrow, it is coming from 4, and the corresponding x is 10. Okay, it is 10. So the value is 0.6 by 15, so 0.04. Okay, now remember, so this value is the b1. Now this value will be your b2. Okay. So this option C will be the correct option. Why this value will be b1? Okay, just remember the matrix. Just remember the matrix. Okay, so if you put x equal to x1, this term will be 0. This is already known, right? So it will be f2 of x1. This 9 is f2 of x1, right? Minus 4 minus f2 of x naught. Yeah, this is 4 divided by x1 minus x naught. Here x1 is 15, x naught is 10. So this term. Okay. Similarly, if you put x equal to x2, you will get this term. If we put just x equal to x2, similarly, no, so sorry, for these two variable, so for these two data sets, you will get a similar kind of expressions, and you need this in order to get the final value of b2. In the terminology of the divided difference formula, here this calculation may not be exactly correct. This final, I may have made some error in this calculation, just check it. But this is the major idea. It simplify your calculation. Okay, but the exact expressions of this, that is simplified in this fashion. The Just a second. Yeah. So b naught is f of x naught. This is just f of x naught. F of b1 is f of x1 x naught. It means it is fx1 minus fx naught by x1 minus x naught. b2 is equal to f x2 x1 x naught. It means that f of, I can write it in this way, f x2 x1 minus f x1 x naught divided by x2 minus x naught, because this is one function, this is similar to another function, and the two limits are x2 minus x naught. I can write this, I can also similarly break this. It will be f of x2 minus f of x1 divided by x2 minus x1 minus f of x1 minus f of x naught divided by x1 minus x naught by x2 minus x naught. So the final expressions is fx2 minus fx1 by x2 minus x1 x2 minus x naught minus fx1 fx naught, sorry, minus f of x naught by x1 minus x naught x2 minus x naught. Now if you just put the values of x1 x2 x1 x2 x naught, you will find that this is the correct answer. So let's just verify that. Or the simplest way is to do the table. I will show some more examples how to use the table, so it will be clear to you. But first let's just verify that if this table is the table that I have made is correct or not. So so I will just put the value. So what is f of x2? F of x2 is your 25. Yeah, so it is 25 minus, or f of x1, f of x1 is 9. So divided by x2 minus x1, that means this two term, x2 minus x1 is 16. No, sorry. I was working on the y terms. Pardon. It will be 25 minus 15. That is x2 minus x1, right? It will be 10 multiplied by x2 minus x naught, 25. 25 minus 10, that is 15, right? So minus f of x1 minus f of x1. So 9 minus 4. So this is 5. And x1 minus x naught. What is x1 minus x naught? X1 minus x naught is 5. And x2 minus x naught is again 15. So this is 150 and this is 75. So the common is 150. So this is 16, right? And it will be 2 into 5, so minus 10. So 6 by 150. So it is equal to 0.04. So the value that we obtained from table is correct. Okay? Okay. Now the next question. Again here also we will use the table. Just a moment. Ah, right. Now here we have given, we are need to find the velocity of a particle. Sorry, we are given a data set. From here I need to calculate the velocity of the particle at t equal to 7. Okay, just a moment, I need to take some water. So in this case, so we can clearly see that my t not equal to 5, right? And t1 is equal to 8. So my dv dt is equal to b1 plus b2 into, so I need to find the value of v here. Just a second. Okay, so here I have made a mistake. I forgot to provide it a table for v. Okay, so let's just assume some values. Okay, then we will proceed. So suppose this is p. So from here I can find the value of t naught and t1. So this is 5. This is 8. And suppose guess. So t2 equal to maybe 12. So this is 12. And let us assume some values of v. Okay. Otherwise, we will not be able to find b1 and b2. So probably b is equal to 1, then 3, and then 7. Okay. So first I need to, so from the table. So here I want to show you how to use the table again. So this value is equal to b naught, right? And now this one. So 3 minus 1, 8 minus 5 is equal to 2/3. And this value is 7 minus 3 by 12 minus 8 equal to 4 by 4, 1. And now, so this value is equal to your b1. And now you just need to calculate the value of b2. That is 1 minus 2 by 3 divided by what I have told in the last question, that you need to follow the arrows. So here 1, it is coming from 7 and the corresponding t is 12. It is 12, 1, 12. And 2/3, it is coming from this 1 and corresponding t is your 5. So it is 1 by 3 divided by 7, to 1 by 21. Okay. So your b0 is 1, right? Yeah. b1 is your 2/3 and b2 is your 1 by 21. So just plug in the values here and calculate dv/dt at t equal to 7. Okay. One point, not interesting, that a crucial point, that just see that here I have given that you need to find the value of t at t equal to 7. So if I put t equal to 9 or t equal to 10, what do you think? What will happen? Will it give me correct answer? The answer is no. Sorry, no, not 9 or 10. If I put t equal to maybe 13, then the answer, it will give me some expression. It will give me some value. It will give me some value of dv/dt. But will it be correct? The answer is no, because my highest range of my t is varying from 5 to 12. So I don't have information beyond that. Okay. So the better, I will be confident about my answer. So for to get the value at t equal to 13, I need to use extrapolation. Okay. But I will be confident about my result from my interpolation thing, that is at t equal to 7. Okay, so this is, so we will solve a similar kind of problem about the range. What should be the proper choice of input values, so that we will be confident about our output result. So the last question deals with this kind of, probably the last question deals with the similar kind of exercise. So we will talk about that there in detail. So now, okay, so this is again an exercise on the divided difference table. So here what we needs to do, that is, okay, so the basic thing is that from the table, from the expression itself, you can very easily say what is your b0, b1, b2. Okay, how can you do that? Just check that this is 5. That means this is x naught. X naught is here. This is x1. X naught is here, x1 is here. And what is the general form? The general form is f2 indicates that, yeah. So here I haven't provided the value here. Okay, but during the process I will be able to figure out what is the value. Hmm. So uh, yeah. So what is the general form of f2x? Here I have three data points, so this is a second order polynomial. So f2 of x, the general form is b naught plus b1 x minus x naught plus b2 x minus x naught and x minus x1. So this is the general form. So b naught, so just compare these two expressions. You will find that b naught is equal to 8, b1 is equal to 4 by 3, and b2 is equal to minus 1 by 42. Now, and when you have got the expression, you just plug in the value of 11 here in this expression. You will be able to find this value. Okay, you will be able to figure out this value, this unknown value. Okay, so let's move on to the next question. I will not, so I haven't done the I haven't solved this using the table, but I have shown you the general form of this divided difference formula for three data points, and completely fits with this structure. And I can you can clearly you can very easily put those values. Okay, so b1 is 4 by 3 for this question. Okay, so this is a conceptual question. So after that, I will start with the Lagrange interpolation. So, so here we are dealing with functions. Okay, but can you assume any function as your interpolating function? The answer is yes. If the function is enough sufficiently differentiable or integrable, you can very easily use any kind of function. Okay, so all of the above can be your suitable choice for interpolating function. But the next obvious question that should come, that why do you use the exponential, sorry, why do you use polynomial function? Because polynomial functions are very easily to deal with. We can very easily differentiate it, integrate it, double differentiate it, anything. The formula is very simple. So polynomial is a very suitable choice, very easy choice for the differential compared to the other three, exponential, trigonometric, or some complicated function. Okay, we can take any functions as my interpolating function, but the polynomial is probably the easiest choice. Okay, now a polynomial passing through u. So here from here, so how many questions do I have? Yeah, so I will solve. Okay, so I only have two. Yeah, I have few questions regarding this Lagrange interpolation. So here you will see that using the divided difference formula is much easier compared to this Lagrange interpolation. So here I have 2 points, u and fu, ufu and vfv. Okay, and this is just a linear interpolation, and I need to find the approximate value. So this is one, not here. So f1 indicates that I have two data points, so I will get a straight line. Okay, now what will be the choice of the straight line? Now what is the formula? F1 of x is equal to y0 L0 of x plus y1 L1 of x. So this is the formula. Remember that L0 of x0 equal to 1, but L0 of x1 equal to 0. Similarly, L1 of x0 is equal to 0 and L1 of x1 equal to 1. The reason I have told just at the beginning of the class. Okay, so for 2 points, this is the formula. Now here I have y0. Y0 is equal to f of u. And L0 of x is equal to x naught, in the denominator it will be x naught minus x1. That means u minus v. And the numerator it will be x minus v. Similarly, y1 is will be your f of v, and L1 of x will be in the denominator, it will be x1 minus x naught, that is v minus u, and in the numerator it will be x minus u. So what will be your f1 of x? F1 of x will be, so what is y naught? So first let me write L naught of x, that is x minus v u minus v f of u plus x minus u v minus u multiplied by what is the value of y1, that is f of v. So this x minus v u minus v f u x minus u by v minus u f v. So this option B is the correct answer. Okay, very easy example. Okay, now here we will exercise how to find how exercise and a complete problem. So how what will be the value of L2 of 13? Okay, so in case of Lagrange interpolation, we cannot we don't have any shortcut like that divided difference formula. We need to do the whole calculation in this fashion. So here we cannot use some similar idea of difference table. We can't do that here. So L2, so L2 of x, L2 of x means in the denominator. So here I have total how many points? 3 points. So it is x naught. This is x1. This is x2. So it will be x2 minus x naught, x2 minus x1 into x minus of x naught, x1. So what will be the value? So it will be x minus 6, x minus 9 divided by x2 minus x naught, that is 9, into x2 minus x1, that is 6 by 54. So 13, so L2 of 13. So 13 minus 6 is 7 into 4 by 54. So it will be 14 by 27. So option A is correct. Yeah. So this is the question where you need to. So previously I was talking about that there should be a range in which your interpolation works. Beyond that limit, the interpolation may not work. Okay. So this is one example. So here where it tells that if you want to find the value of fx at x equal to 11 using a quadratic interpolation scheme from the following data points. Okay, you have many data points. Then what should be the correct choice of x values? So so here you need to first think that what is the order of the polynomial. The question says that it is a quadratic polynomial. That means you need 3 data points. So you need total 3 data points, and what should be a proper choice? So let's go part by part. The one choice is 3, 6, 9. Huh. So 3, 6, 9. But here you need to find the value at 11. It doesn't bracket this x equal to 11 point. So this cannot. So I have no guarantee that this polynomial will go through this x equal to 11 point. Okay, I have no idea about that. Okay, so this is extrapolation. So this should not be a correct choice. Now the second option is 6, 9 and 15. So 6, 9 and 15, right? So here this point brackets this point x equal to 11. Okay, so 11 is greater than 6, greater than 9 and less than 15. Okay, so this can be a suitable choice. Also, the last option, also there can be another option. So now let's ask the question. So here I haven't provided the option, but I should have done that. So here the one more option choice can be. So one option is 6, 9, 15. I can see that 11 lies in this range, 6 and 15. So this is one suitable choice. Now what about this point 9, 15 and 18? Is it a good choice? Now x equal to 11 lies in this limit. It is true, but you need to verify. you need to find a difference between the starting point and your starting point, end point, and your desired point x equal to 11. So in this case, okay, so 11 minus 6 equal to 5, that is the that is the x0, the x start, and 11 minus 15, I just need to take the module, the absolute value is equal to 4. So it is different from the starting point is 4 and the ending point is 4. 5 and ending point is 4. But here its difference with the ending point is 7, which is sufficiently large, okay, compared to these two. So this option should be a desired choice, not this option, right? And the third option is 15, 18, and 20. So this is a trivial situation that 11 doesn't belong to this range. So this is not a good choice. So option B is the good choice. Okay, I hope this idea of the range is clear to you. All right. Okay, so this is a question from the previous year assignment. So following table gives the population data of a city from the year 2000 to 2015. So this is the year and this is the population. This population is in million. Okay. Now, so I have used Li, L0, L1, L2. Here in this question, it is given as K0, K1. It should be K2. K0, K1, K2. Okay. Now it says that you need to calculate the value of K naught of X. Okay. So K naught of X, very simple. K naught of X. So it is 0. So K0, that means X0 minus X1, X0 minus X2. How many data points? 1, 2, 3, 4. X0 minus and there will be X0 minus X3. And in the numerator, I will have, so it will be X minus X1, X minus X2, and X minus X3. So what will be the final solution? So your x1 is 2005. So x minus 2005, 2010, 2015. X minus 2010, x minus 2015 divided by x naught minus x1. That is x naught minus x1 is this, minus 5 into minus 10 into minus 15. So in the denominator it will be minus, sorry, so in the denominator it will be minus 750. Okay, and this and numerator will be this. So this option A is the correct option. Okay. Okay. So here you need to find a complete solution using the divided difference formula. Okay. So first, so I will again take help of the table. So let me first write down the data. So this is x, this is y. X is 0, 6, 20, and 45. 0, 6, 20, and 45. And y is 30, 48, 88, and 238. Just give me 2 minutes. Huh? Okay, so let's start with the problem again. So the first difference is 48 minus 30 by 6 minus 0. So that is okay, so 30. So it is 18 by 6 is equal to 3. This value is equal to 88 minus 48, that is 40, and 20 minus 16, it is 40 by 16. Sorry, it's 40 by 14, which is equal to, just a moment, let me use my calculator. So it is 40 by 14, it is 2.86 approximately. And this value is 238 minus 88 is 150 divided by 25 is equal to 6. Now, so you need to find a value between y15. So one easiest thing you can do that. So yeah, so here it is an interesting thing. So, I will complete the difference table anyway. But see that your 50, you have this point 15. Hmm. So you have total 4 points. So it is up to you. So what will be the order of the polynomial? Your 15 lies between 6 and 12, 20. You can work on this. You can work on this too with these 2 points. You can work if you want a quadratic polynomial. You can work with these points. Okay, 0, 6, and 20 because 45 is far away. Okay, and if you want a cubic polynomial, then you will also include this point as well. All right. So let me just finish this table. Then first I will work with this linear interpolation. Later I will show an example where you need to solve both linear divided difference and quadratic divided difference as well. Okay, so just here I will just complete the table and I will proceed with the linear divided difference formula. So here, so 2 points, so the numerator is easy, 2.86 minus 3, and denominator is just follow the arrow. It is coming from 20, right? Yeah, it is coming from 20, and this 3 is coming from x equal to 0. Okay, so it is 2.86 minus 3 by 20 equal to minus 0.007, and this value, this is 6, so it is 6 minus, so it is coming from 45, and this 2.86, just follow the arrow, it is coming from 6. Okay, so 6 minus 2.86 divided by 45 minus 6, that is 39, so it is 0.0805, and the final answer is here the denominator will be 45 minus 0, because just to follow the arrow, it is going towards 6 is going to 238, and the corresponding x is 45, and 0 minus 0.007 in the arrow directions towards 3, then towards 30, and the corresponding x is 0. Okay, so the final result will be 0, so this is plus. So 0.0805 plus 0.007 divided by 45. So this will be your answer. So here it will be your f of x0. This is your f of x1 x0. This is your f of x2 x1 x0. And this will be your f of x3 x2 x1 x0. B0, B1, B2, B3. All right. Now, if now my target is to construct a linear divided difference interpolation. Okay. So here I have just two data points, 6 and 20. and the values are 48 and 88. Why? 48, 88. Sorry. So what will be the case? 40 by 40 is equal to what? So I have probably done this value. Yeah, 2.86. So what will be your final solution? Final solution will be if one of x is equal to b naught. B naught is this value 48 plus b1 this value x minus x naught. What is x naught? X naught is your 6. So 48 plus 2.86 into x minus 6. Now you need to find a value at x equal to 15. So f1 of 15 is equal to 48 plus 2.86 into 9, and the value is 7 is near 73, is approximately 74, 73. Okay, so this is the result. Now, just a moment. Okay, now this function, again you need to use divided difference formula here. So x and y, and it says that you need to find the value of sine pi by 6. Now pi by 6 lies between 0 and pi by 4. So here this is a, so this I have only three data points. So here I will try both the linear interpolation and the quadratic interpolation. Okay, because because I know what is the value of sine pi by 6. Okay, and I can very easily verify with it. So first, just a second. Sine pi by 6. Sine. Okay. All right. So this this pi by 6 is lies between 0 and pi by 4, right? So pi by 6 is 180 and pi by 4 is 45. So it lies between 0 and pi by 4. So one is 0, another is pi by 4, y is 0 and 0.7071. So what? So this is your b0, and what is your b1? That is 0.7071 into 4 divided by pi, that is 0.9003. So what is the solution of your y? So f1 of pi by 6, that is the approximation of sine pi by 6 value, is equal to b0, b0 is 0, plus b1 0.9003 multiplied by x minus x naught, that means pi by 6 minus 0, so is equal to 0.9003 into pi by 6. So it gives me the value of 0.4714. Okay. Now, if I use three data points, okay, then what will we get? So I need, so here I am keeping it here, okay, and I have the value at pi by 2. So pi by 2, the value is 1. So this difference is point, so 1 minus 0.7071 into 4 divided by pi. Okay, because pi by 2 minus pi by 4 is pi by 4. So this value is 0.3729. Now I need to define the difference between these two. So the final, so the f of x2, so this is your b1, this value is 0.9003, and b2 will be 0.3729 by 0.9003 divided by pi by 2, right? So, so the value will be 0.3729 minus 0.9003 into 2 by pi. So this value is minus 0.3357. So what is the value of y of, sorry, f2 of pi by 6? That is, the first value is b0 is 0, equal to 0.9003 into pi by 6, that is x minus x naught, minus 0.3357 into x minus x naught into what value? Into x minus x1, right? That is minus, so pi by, so that is pi by 6 minus pi by 4. That means it is minus pi by 12, right? Yeah, so this is minus pi by 12. So we need to do the calculation here, right? So 0.9003 into pi divided by 6. So first term I have already got, that is 0.4714, and it will be a plus 0.3357 into pi square, right? Pi square divided by 72 plus 0.4714. Yeah, plus some value. So finally, sorry, the not some value, it is 0.04601. It will be 5174. Now sine pi by 6 is equal to 0.5, and you can see, if you calculate the error, this is much closer to this 0.5 compared to this linear interpolation result 0.4714. So if you increase your order of interpolation up to some limit, the value will be more and more accurate. I have so I have said the term up to some limit very carefully, because we will deal about some situations where if I increase the number of data points as well as the order of the polynomials, it will not reduce the error. That's why the spline interpolation comes into a picture, which we will deal about it next. Okay, so right. So before that, so I will talk about the spline interpolation. But before that, we need to solve this problem. Complete. We need to solve this problem. Okay, using both Lagrange interpolation and a divided difference formula, using both linear and a quadratic interpolation. Okay, so this will sum up our all these exercises. Okay, so this question 12 based on the Lagrange interpolation, and question 3 based on the divided difference. These two are a little bit lengthy questions, but this will worth it, because you will get, but because here I will deal with the difference table and the Lagrange interpolation, the polynomial functions. So you need to get the detailed idea of this thing, and after this I will start with discussing about the spline interpolation. Okay, so here it says that, yeah, so first let's solve the easiest thing, that is the linear interpolation. So first I will Li is the Lagrange interpolation. Okay, so the linear, I have data points of x and y. Now 0.644 lies between 0.64 and 65. Okay, so let's use that. So 0.64, its value is 1.896481, and 0.65, its value is 1.915541. Okay, so what is the value? So what will be the value of the L naught x? L naught x will be, so it will be x naught minus x one, right? Because it's 0 here. So it will, in the denominator, it will start with the x naught. So x naught is your 0.64 minus 0.65, and it will be x minus 0.65. And what will be your L1? With the so let me write down the formula as well. It is y naught L naught x plus y1 of L1 x. L1 of x. Here we will see that compared to the divided difference using this Lagrange interpolation is quite complicated, because you need to do you need to a good amount of task to get the same answer. Okay, this is a good exercise for that. This question 13 and 14. This is a good exercise for. So it will be x minus 0.64 divided by 0.65 minus 0.64. Okay. Now f1 0.644. Pardon. So why not? Why not is 1.896481 into L naught of x. So it will be 0.644 minus 0.65 divided by 0.64 minus 0.65 plus y1 1.915541 multiplied by 0.644 minus 0.64 divided by 0.65 minus 0.64. Now you need to do this calculation. So I have already done the calculation. So you will find that 1.904105. Okay, you will find this answer. Just do this. Okay, and verify if it is correct. I hope this is correct. Now, let me write down the exact expression of the up to some decimal points, the exact expression of exponential 0.644. It is 1.9040819. Okay, and this linear interpolation does a pretty good job. It's up to 3 decimal points it is guessing the correct answer, but not after that. Okay, now let's solve it using the quadratic Lagrange interpolation. Okay, so this quadratic. So here you need to make a choice here. Okay, this point is 0.63 and your data point is 0.644. So the difference is 0.014. But you can also make this as a choice. But here the difference is 0.016, which is larger. So I am taking these 3 points, 0.63, 0.64 and 0.65 to find a value at 0.644. So at 0.63, the value is 1.877610. So from the I am getting this from the table, this, and I have already written the value of 0.6 at 0.64 and 0.65. Okay, so just 0.64 and 0.65. I'll get some values. So my L naught of x will be x0 minus x1. The denominator, it will be x0 minus x1 into x0 minus x2. x0 minus x1 multiplied by x0 minus x2, and in the numerator it will be x1 x minus x1 and x minus of x2. So if I put the values, it will be x minus 0.64, x minus 0.65 divided by 0.63 minus 0.64 into 0.63 minus 0.65. This is L naught x. Similarly, if you do if you find a value expression of L1x, I am just I don't have I don't have enough time, so I am complete so I am directly writing down the expression of L1 of x. So it will be, we will find that it will be x minus 0.63, x minus 0.65 divided by 0.64 minus 0.63 and 0.64 minus 0.65. This is x0 minus this is x1 minus x0 and x1 minus x2. Similarly, you will get that L2 of x equal to x minus 0.63, x minus 0.65, 0.65 minus 0.63, and 0.65 minus 0.64. You can already see that this this job using this interpolation scheme is already lengthy. Okay, now you need to find the value of y of x, and that is L0 of x into y0 of x, that is 1.877610 plus L1 of x into 1.896481 plus L2 of x into 1.1 sorry 915541. Right, now if you put x equal to 0.644, you will find that L naught of x is equal to minus 0.12. L1 of x is 0.84. Now can you guess without doing anything the value of L2x? The value of L2x is equal to 0.28. Remember that in the at the so in the so earlier I have told that summation for any set of data points, it should be true that I equal to when Li of x is equal to 1, and I have shown it for n equal to 2. Here L0x is minus 0.12. L1 of x is 0.84, so it is 0.72. But the summation needs to be plus 1. So L2, so this is the only choice. If you put the value of x equal to 0.644, you will get exactly the same answer. Okay. Now, if you put these values here in this expression, you will find that y of f2 of 0.644 is equal to 1.90408.232. So previously for the linear scheme, it is corrected up to 3 decimal points. Now it is corrected up to 5 decimal points. Okay, you can see, yeah, now it is corrected up to 5 decimal points. Okay, so this is the improvement. Now I can do the same thing using the divided difference, and I can do and I will show that I can do it more easily. Okay, so let's do that. Just a moment. Okay. So I will not go over why we will choose this limit 0.64 and 0.65, because it brackets to 0.644. I will not talk about the range here. I will just show the calculation. Okay, the why we in the quadratic we will choose 0.63, 0.64, and 0.65, these 3 points, and I have already clarified the reason in the Li technique. So here is 0.64, 0.65. So 1.896481, 1.915541. I need to just do value calculate it. So this is b naught, and I just need to find this value. Okay, so which can be very easily done using in your calculator. You will so what is the value? So what will be the value for that? In just a moment. Mm, right. So it will be 1.915541 minus 1.896 6481 divided by 0.65 minus 0.64 is 0.01, right? So it is 0.01. So this value is 1.906. Okay, so what is y of 0.644 is equal to 1.896481, which is this value, plus 1.906 into 0.644 minus 0.64. So into 0.644 minus 0.64 plus 1.896481. So it is 1.904105, corrected up to 3 decimal places. See, this is just a two-line calculation compared to all the lengthy calculation, even in this LI technique, even in the linear scheme. Now, similarly, you can find the solution very easily for the quadratic. If you want to want a more accurate result, go for the quadratic solution. So, what will be the so? Let me. I will just construct a table. So it is 0.63, 0.64, 0.65. This value is 1.87761 not. Yeah, the 0 at 0.64, the value is 1.896481. It is 1.915541. Okay, so this value is your b naught. Now if you use divided difference, you will find that this value will be 1.8871. I have already done the calculation, so I am just writing down the final result. Okay, so it will be 1.906. This is your B1, and this will be your 0.945. Remember that you need to follow the arrow. So here it will be 1.896481 minus this term divided by 0.64 minus 0.63. So the first term is easy. The problem comes in the second term. Here unit, so it will be 1.906 minus 1.8871 divided by what will be the denominator. The denominator, for the denominator you need to follow the arrow. It is coming from 1 point, so this minus this, so first the denominator corresponding to this term, this will come. So it will be 1.906. It is coming from this term, and the corresponding x is 0.65. Similarly, it is coming from the 1.8877. It is coming from this term, and it is the corresponding x is 0.63. So it will be divided by 0.65 minus 0.63. The same idea. So finally, we'll get this result, and this is your B2. And your y 0.644, you just need to put the value b0 plus, let me just write down the final expression, 1.877610 plus 1.8871 x minus x naught, that is 0.644 minus 0.63 plus 0.945, 0.644 minus 0.63, 0.644 minus 0.64. You will get 1.9048232. This is exactly the same answer that we got in the previous method. Here also I have got exactly the same answer, but here you you can see that the calculation is much easier here. Okay, so it is always better to use the divided difference formula in order to solve this kind of problems. Okay, now So I have told that if I increase the order of the polynomial, okay, it is not always guaranteed that I will find a good solution always. Okay, so if I have a function like this, that is y equal to 1 by 1 plus 25 of x square. Hmm. So I will show a animation. So this is a Wolfram animation. So you will see there that if I increase the polynomial, see, this n is indicates the order of the polynomial. If I increase this n, that means if I include more and more data point to my data set, okay. So the function looks something like this, similar to like this. You will see the exact function in the animation. So suppose I have total 4 points, and I will get and some approximate match. This is not a good match. But if I so it is so you will see that if you increase your data points, if you increase your data points, that means the order of the polynomial will increase, but it will never reach a good match. Okay. In this kind of situation, we need to consider about the spline interpolation, where we deal with the piecewise data, not the entire data field. Okay, but first, before going into that thing, let us first see the animation. Okay, this is an interesting animation. So just a moment. Yeah. Let me just refresh it. Just a moment. Yeah. So I think you can see it. Yeah, you can. I think you can see it clearly. So here, this is a slider. Okay, I can increase the number of data points. I can increase the number of data points from here. Okay, I will use this thing equally spaced. Yeah, fine. So initially I have total 5 data points, and here it shows the absolute error. Okay, absolute error between the approximate polynomial and the exact function. This function is 1 by 1 plus, so here it is clearly written that it is 1 by 1 plus 25 of x square. Okay, this is the function. Now, so our previous idea so far told that if I increase the data point, the approximation is getting better. So in case of e to the power x, the linear interpolation is weaker than the quadratic interpolation. Okay, but here if I increase the data point, now the data point is 15. You can see that locally it is agreeing with the solution, but if I go further and further from this x equal to 0 line, the error is increasing. And you can see here the error at the edge, it is approximately, it is almost 7. Okay, which is sufficiently large. That means the solution is that means that our fitting polynomial is diverging. So if I increase even more, you can see that now the error is 8. Now the data points are 20. Now here the data points are 20. Okay, now if I increase it further, 35, you can see that error is increasing. Now the error is 10,000. So it is not always a good idea to abruptly increase the order of polynomial. Okay, in this kind of situation, we need to use the spline interpolation. Okay, spline interpolation is it is already very it is already discussed in the class, where we deal with the piecewise data points. Okay, so now let's go back to our calculation. Right. So, in case of spline interpolation, suppose you have some discrete data points like this, 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 this. You need to, here in this case, we consider only this point. Okay, then this. then this. We proceed piecewise. Okay. It has also different types: linear, quadratic, cubic. Just a second. So here I can also, I can also fit some straight for the linear. I can fit some straight line for this different data points. I will solve a problem for the linear interpolation for the linear spline. So suppose I have some data points x naught, y naught, x1, y1 up to xn and yn. Okay, so I can fit some polynomial for this. So suppose my f1 of ax equal to b naught plus b1 x minus x naught when a6 less than or equal to x1 x naught. Similarly, f2 of x, so this is b naught 1, b1 1, b0 2 plus b1 of 2 x minus x1. It is x less than of x2, x less than of x2. This is not valid here. Okay, similarly, I can write for fn of x, b0 of n plus b1 of n x minus x n minus 1, where x is less than or equal to xn and xn minus 1. So this is the linear spline. Now here is a problem. The problem appears at the connecting points. So there is a sharp change in the slope. It will affect your final result. Okay. Now in order to avoid that, what we can do, we can equate the slope. Okay. Now if I calculate the slope here, it is just a constant. So what will be the next choice? The next choice will be a quadratic polynomial, right? So it will be b naught plus b1 x minus x naught plus b2 x minus x naught and x minus x1. So this will be the next obvious choice, which will ensure that the slope at this point will be same. So if I want to modify, if I want to get a better approximation, I can do that. The slope at this point will be zero. Also, the second derivative at this point will be also zero. Okay. So now what function can ensure that? That is a cubic polynomial, ax cubed plus bx squared plus cx plus d. This kind of polynomial, it will ensure that this slope at the joining point, the second derivative also equal. Okay, not zero, equal. Okay. So now in this slide, now let's solve this problem. In cubic spline interpolation, which spline derivatives must be continuous at the interior points? Third derivatives, first and second derivatives, none of this. So obviously this will be the choice. Okay, so this should be your answer. So first and the second derivative should be equal. It should be continuous. Okay, at this interior points. Now, so this is the last question of today's live session. So this is related to the linear spline. All right. Okay. So the equation of linear splines are x. Okay. So I have provided a data set. Now you need to find you need to find a correct answer among these. Okay. So now let's work with this. So okay. So I don't have a sufficient space. Oh yeah, but I can work here. So x, and this is f of x. This is 3.0. I need to do, this is 4.5. This is 7.0, and this is 9.0. This 2.5, 1.0, 0.0, again 2.5 and 0.5. Now the first line, the first function, the first linear, the straight line will be valid for x naught and x1. Okay, so here I am taking so I just need b naught and b1 for each of these cases. Okay, so here it will be 1.0 minus 2.5 is minus 1.5 divided by 4.5 by 3.0, so the result is minus 1. All right, here it is 2.5 minus 1.0, this is 1.5 divided by 7.0 minus 4.5, 2.5, that is 0.6, and this it is minus 2 divided by plus 2, so it is again minus 1. I don't need to find the other b2. Okay, so the first polynomial, so let's skip the term polynomial, the first straight line. Okay, for the first straight line, that is x1 of x, it will be valid in this limit x1 and x naught. So it will be b naught of 1 plus b1 of 1 x minus x naught. Now what is b naught of 1? B naught of 1 is this value, right? It will do 2.5 plus b1 of 1 is minus 1 minus x naught. What is x naught? It is 3. So minus x minus 3. Now what is s2 of x? So how many straight lines that we can draw? So x naught and x1, x1 and x2, and x2 and x3. Okay, so three different straight lines we can draw. So if I simplify it, it will be 5.5 minus s x. So this is s1 of x. It now s2 of x, it will be valid. So it is valid when x is less than or equal to x2 and greater than or equal to x1. Okay. So s2 of x is equal to b naught of 2 plus b1 of 2 x minus x1. Now b naught of 2 is this value plus 1 plus b1 of 2 is 0.6 into x minus x1. x1 is minus 4.5. Yeah. So if I simplify it, I will get 0.6 x minus 1.7. Yeah. Now s3 of x is equal to b naught of 3 plus b1 of 3 x minus x2. This will be valid when x is less than or equal to x3 and greater than or equal to x2, right? So it will be b naught of 3. B naught of 3 is this term 2.5 plus b1 of 3 is minus 1. This is minus 1 into x minus x2. x2 is your 7. Yeah, x minus 7. So it is 9.5 minus x. So in the first option, it is x1 x is minus x plus 5.5. Yeah, 0.66 plus 1.7 plus 1.7. No. It should be minus 1.7. Yeah, this should be minus 1.7. Minus 1.7, and s3x is minus x plus 9.5. Yeah, so this option is correct. So this is just a mistake. I think it should be 0.66 minus 1.7. Okay, now s1 of 3.5, what is x1? So it should be 2, right? And s2 of 5, it will be 3 for 0.6 into 5, 3 minus 1.7 is 1.3. So this is also correct. So that means it should be minus, right? So option 1 is correct, option 2 is correct, option 3 is also correct. That means all of them are correct. Okay. So this is the basic idea of the spline interpolation. The similar thing can be done for the quadratic and the cubic case also, but the calculation will be lengthier. Okay, but the basic idea is we divide the whole data set piece by piece and try to fit the polynomial in each case of data set, and we connect each data set. Okay, in case of linear polynomial, with the value at the connecting point should be equal. In case of quadratic polynomial, the value as well as the slope at the connecting point is equal, and the for the cubic polynomial, the value, the slope, and the second derivative is will be equal at the connecting point. Okay, so that's all for today. So we will meet in the next class, and good night.